Hey guys, it's Mr. Sheeline here. This is going to be the notes for the 4.2 notes classifying chemical reactions. Again, just to remind you guys, if you've already forgotten from the last set of notes, just remember that I'm giving you guys the full set of notes all filled out already in PDF form, and maybe whatever other form I may come up with in the future. Just because I'm pre-recording this, it's possible some things may change. But just remember, initially I'm giving you guys the full filled out notes. So all it is up for you to do is hopefully you can print these out. You can write all these notes out on a notebook, or just have them available and be able to read them electronically on your Chromebook. So okay, so let's get to it. So there really isn't any calculations for the set of notes. It's more about terms. It's more about understanding certain kinds of chemical reactions, and we break them down into more or less like 5 different groups, and then there's some distinctions in one of the groups, like meaning we've got 2 different kinds in one particular group. So this one I'm actually going to highlight a little bit just so it's we can read these clearer. And I'm going to go through real quick on the specific kinds of reactions that you need to know, okay? And then we'll kind of walk through them a little bit. I'll mainly just be going through over these examples to really point out like how is it that you can read these. So this first one here is going to be like a synthesis reaction, which is also just called a direct combination reaction, okay? So you need to know this guy. There's something called decomposition reactions, so you need to know this guy. And then this is one that has 2 different forms. So they're called single replacement reactions. Now the only thing is that, like I said, there's 2 forms. So the first form is going to be a cationic single replacement reaction, and then there's an anionic single replacement reaction. I'll just tell you that these 2 are the most commonly confused reactions, and if you get these 2 down, you're golden as far as understanding the difference between them. And then you also know the other ones, like 100%, you're golden. Just make sure you lock down the differences between the 2. Don't end up like my students did last year and have a lot of issues with it. Get it over with now, understand the differences between the 2, and you'll be set. Then there's a double replacement reaction, okay? I'll highlight that guy. You got to know this guy. And then under like this unique reactions, yes, it is unique, but you'll be seeing it a lot. And they're combustion reactions, okay? And of course, if you know what the term combustion is as if, something catching fire, okay? So we'll be kind of looking at these examples, and again, I highlighted these because you've got to know these. You've got to know what they're called, and you need to then know their definitions and their examples here. Okay, so here's the definition, but I'm more interested in showing you here, like when you see a synthesis reaction, this should be one of the easiest ones to find. All it is that you have like 2 or more products, 2 or more substances on the reactant side, and then you've got 1 compound on the product side. So looking at it here, if I were to say that like products are blue and then reactants are red, and I know on the screen it won't look really red, okay, here are your reactants, here's your product. Reactants and then product. Okay, notice it's like A plus X is equal to, or yields AX. 2 atoms of iron combines with oxygen or reacts with oxygen gas and yields two molecules, or 2 formula units of iron oxide. Okay, like that's synthesis. Taking 2 things, sticking them together, and yielding 1 product. That is a synthesis reaction. And the same thing applies down here. It's just bigger. Okay, so it would be like A plus BX yields BXA, or 3 molecules of oxygen gas combined with potassium chloride, two formula units of potassium chloride, to yield 2 formula units of potassium carbonate, or chlorate, chlorate. Okay, so again, you're starting with two things, A plus BX, yielding BXA. Basically, everything is combined into one product. So if you see one product, it's a synthesis direct combination reaction. Easy peasy. Decomposition, however, is the complete opposite. So reactants will still be red, products will still be blue. Okay, and I'll even write this note. Opposite of synthesis. So this guy starts off with one compound, but then breaks up into two or more. So it'd be like AX yields, decomposes into A plus X. Okay, or ammonia here breaks down two formula units of ammonia, not ammonium, ammonia breaks down and decomposes into nitrogen gas and three molecules of hydrogen gas. Okay, these are still our reactants, and these are still our products. Okay, because remember, it's not about how many things you start with and end with. It's more about, okay, what are we starting with and what did we end with, not the quantity. Okay, there's a distinction. And it'd be like this down here. Okay. So here we've got hydrogen, hydrogen peroxide. So AX yields AX plus X. So in this case, hydrogen peroxide decomposes to form water and oxygen gas. Okay, decomposing. Okay, decomposition reaction. It's the complete opposite of synthesis. Start with one thing, you end with many. Synthesis, you start with many, end with one. Easy enough. Here's, again, and then we're going to be really focusing on this because, again, I don't know why, but kids just have, you guys have, students have a lot of issues with remembering cationic versus anionic single replacement. Okay, so before we get into what the difference is, or what this type of reaction looks like, you've got to remember, cation is going to be the first listed ion in a compound. So if you have something like, let's say, iron oxide, okay, if you've got something iron 2 oxide here, which one is your cation and which one is your anion? Okay, and you should know this is your, I almost wrote wrong thing, that your iron is your cation, oxygen is your anion. Cations first, anion second. Okay, so when it comes to these two, in order to understand the difference between them, you have to remember what an anion is and what a cation is. So if you don't remember what that is, you better be working your tail off to remember which one's which. Because if you don't, you're kind of screwed. You can say it's a single replacement, but if you don't tell me if it's an anionic or a cationic single replacement, I can't give you the points for that. I've got to know, is it the cationic or anionic single replacement? Okay, so let's take a look at this. So real quick, both of them, though, they're going to have one or more, or one compound and one element, and then their product is going to be one compound and one element. Okay, they're not going to be the same compounds, and they're not going to be the same elements on the reactants and product side. Okay, and we'll see that. So the cationic would be laid out like this. So you've got A plus BX yields B plus AX. Okay, and we'd say, again, this is cationic. How do we know it's cationic? If we look at the X here, because we see the X is always combined with somebody. Okay, and the X is combined with somebody here. And because it's the X is always second, that tells us that the X is always the anion. So then what changes? What changes is the cation that the X bonds to. And so when the cation changes, that tells us, oh, the cations are switching. The cations are being replaced. Okay, so if you see the cation in your product side, if that's the one that's changed, it's a cationic single replacement. Okay, which is different from anionic, which hopefully you now see what the distinction is. If you have, like, say, y plus ax yields x plus ay, okay, notice the A is always bonded. Where's the A? Oh, it's the cation. And if we notice here, the X is swapped out with the Y. Okay, well, the X and the Y were the second ones listed both times. So that tells us then that the X and the Y are anionic. And if that's true, then it's an anionic single replacement. So when we're looking at single replacements, always think which one's being replaced. So if the cation was replaced in the compound, then it's a cationic single replacement reaction. If the anion is the one that's being replaced, also in the compounds, both on the reactant if the anion is the one that's being replaced on the product side, then it's an anionic single replacement. So make sure you understand the distinction and that you understand what to look for. And then here are just two examples of what that would look like. So this would be like magnesium wants to react with sodium oxide, and so it does. And what that produces is it produces sodium. It'll produce sodium probably as a precipitate. It'll produce sodium and then magnesium oxide. Okay. And then over here, and again, notice magnesium is A, sodium is B, X, and then oxygen is X. So the magnesium switches with the magnesium switches with the sodium, so the sodium gets booted out, and then the magnesium is now bonded with the oxygen. Down here, we've got chlorine gas reacts with sodium sulfide, okay, which then produces sulfur, okay, and then plus 2NaCl, which is sodium chloride, just table salt. But notice who gets bumped out. So we have in the compound here, we've got sodium sulfide. Chlorine gas comes in, is like boots sulfur out. He's like, nah, man, that's my boo, and he boots out sulfur, and then he takes the spot. But it's the second spot, so it's an anionic spot, meaning it's an anionic single replacement. Okay. So again, if you still have some issues here, got to address them. You got to talk to me. You need to study up on remembering which one's the cation, which one's the anion. Then there's double replacement reactions. Now these are fairly easy to see. The only thing that will kind of trip you up with double replacement is combustion, just because they can both be quite lengthy. So what is double replacement? Well, hopefully if you after going through single, you probably understand what double is, or at least have an expectation. So in the reactant side, we'll have two compounds, and in the product side, we'll also have two compounds. So it would be to say like AY plus BX will yield 8X plus BY. Okay, so what happened? Well, it looks like here the X and the Y just switch spots. Okay, so instead of one compound and one molecule and somebody switching places with one another, it's two compounds. And you have two elements that are going to be switching each other's places. So in this case, X and Y switch places. Okay, so it would look like this. You'd have sodium phosphate here is going to react with aluminum oxide. And this is going to yield for us some sodium oxide and then aluminum phosphate. Okay, so notice who switched. So it looks like here, and this is going to be that half is, or the glass is half empty or half full kind of scenario. Who switches with who? Doesn't really matter as long as you notice that, sodium started off being bonded with phosphate, but then on the product side is now with oxygen. Aluminum started off bonded with oxygen, but is now bonded with phosphate. Okay, so two people switch spots with one another. Okay, so either you can say, well, the sodium swapped with the aluminum, or phosphate swapped with oxygen. It doesn't really matter. Just know that you have two elements or two compounds possibly switching spots. In this case, phosphate switched with oxygen, or sodium swapped with aluminum. So arguably, it does actually matter. It's the anions that are swapping, but as far as we're practicing it, it doesn't matter as long as you recognize that it's a double replacement, that two things are being replaced, that they're swapping. And then there's the combustion. So like I said, combustion, yes, it's unique, but that doesn't make it rare. So you'll be seeing combustion a lot. Combustion reactions are with hydrocarbons. And the thing that you just, number one, have to look out for is this. If you see this at the end of your, if it's mentioned or if you see it, at the end of your reaction that you have carbon dioxide and water, every single time, 100%, every single time it's combustion. Okay. Another good, so I'll say this, yeah. Every time combustion. Every time combustion. It even says so right here. Products of this reaction include carbon dioxide and water. If you've got carbon dioxide and water at the end in your products, it's combustion. Now, it is possible that in a combustion you're still left with like another material. It is possible. It's still combustion. Okay. A good way to see this is that for the most part, if most of the material you're working with is carbon, hydrogen, and oxygen, it's for the most part, it's going to be combustion. It's not true every time, but for the most part, it's pretty much true. So anyway, this is what you have to look out for. Look out for the carbon dioxide and the water. They have to be both in here to call it a combustion. And they're arguably the easiest to pick out. Easiest to pick out. On top of that, in word problems, it'll tell you that this stuff will combust and will produce carbon dioxide and water. This stuff will burn. This stuff will catch on fire. You know, it will have that language. So it's pretty easy to know, you know, which one's which. Okay? So those are the notes there. So if you guys still have any questions for me, make sure you reach out to me. Thanks for watching the video, guys, and I'll see you in the next one.